Okay, so with Bayesian, so this is just kind of a review. Bayesian review. All right. So the idea behind Bayesian statistics is we want to make inferences about model parameters based on the data we have observed. Okay. So we will, we define theta as the model parameters. Okay, and we will say, we can say x is our data, right? And so what we want is theta given x. This is the distribution of the model parameters theta given the observed data x. Okay. And the key part about Bayesian statistics is that the conclusions we're making about the model or the population or whatever it is that you want to talk about, the conclusion is a distribution. Okay, so the conclusion of Bayesian statistics. How do I spell this? The conclusion is a distribution, not a point estimate. Okay. In contrast to frequentist statistics, in frequentist statistics we treat a parameter, the population parameter, as a fixed value. Okay, so in frequentist statistics we treat the parameter as a fixed but unknown value. Okay, so there's, in frequentist statistics, the mean of the population is some fixed value. We might not know what the mean of that population is, but we don't set a distribution about it, right? In frequentist statistics, we make confidence intervals, and it's incorrect for us to say there's a 95% probability that the mean of the population is between here and here, because there is no probability associated with the mean of the population. It's a fixed value, right? Whereas in Bayesian statistics, the conclusion is a distribution, and we just have a kind of a range where we think theta is most likely to exist. So so the conclusion is a distribution, not a point estimate. All right, and so just let me just contrast. So in frequentist statistics, we might say, if we flip a coin 100 times and it lands heads 61 times, okay, we can estimate theta, or in this case, which would be the probability of heads for flipping a coin, and we can say the probability, our estimate, theta hat is going to be equal to argmax for the likelihood of our data. Right? So this is maximum likelihood estimation. Okay. And so, for a coin flip, this is what a Bernoulli. So we say x is equal to theta to the x and 1 minus theta to the 1 minus x. This is, I'm sorry, this is probability of x. Probability of getting, heads is this theta to the x times 1 minus theta to the 1 minus x, and thus, if you have a sequence of flips, you have 1, 0, 0, 1, 1, etc., etc., etc. We can define we can let z equal to the sum of our x's, okay, and then n is just the number of flips. So in our case, we have z is equal to 61 and n is equal to 100, right? And so the likelihood of our data is going to be the the product of basically our Bernoullis, which will equal theta to the z times 1 minus theta to the n minus c. All right, is this okay? And then, we would try to, we maximize, we find the theta that maximizes this thing, right? Okay, and then, if you do the calculus, or, you could solve it numerically, you'd get the best estimate that's going to maximize this. If z is equal to 61 and n is equal to 100, is going to be 0.61. And that would be our estimate for the proportion that the coin lands heads based on the data that we've seen in maximum likelihood estimation, which would, in this case, would be frequentist based. Is that all right? Did I do this too quickly, or is this okay? I'm getting no reaction from, I'm just getting blank looks on your face. But yeah.
Why is the theta the maximum likelihood happen to be like just 61 out of 100?
Oh man, you're gonna make me do this. So we can. Can I just draw it on the computer? Let's see. You would take the derivative of this with respect to theta, and then you set that equal to 0, and then you maximize it, and then it turns out that the spot where it maximizes is when it's equal to z over n. Okay, and yeah, you'll do the log. It works. Yeah, it works best if you do the log. So you do the log, you take the, and then where you maximize the log likelihood, it also maximizes the likelihood because the log is monotonically increasing. You probably had to do this in 100B, right? You should have. Okay, maybe we don't remember, but okay. And so this is kind of how we can do it in R. We can just say, all right. We can say, what is the if I flip it, if I get 61 heads and I flipped it 100 times, and the probability of the coin landing heads is 0.5, what's the probability that this is going to happen? This happens with a, the density there is 0.007. Okay. This is actually the mass function, probability mass function, not density. And then if the probability is 0.55, it's going to be higher. And if the probability of landing heads is 0.6, it's even higher. It's a 0.0798. And if I say the probability of heads is 0.61, it's 0.0815. And if I, venture away, it starts to go down again. Okay. And so we can actually plot all of this, and I can say, I can vary p from 0 to 1 in increments of 0.001, and I can calculate all of these different values. So instead of me just manually typing in 0.5 and 0.6 and all of that, the computer will do it for everything from 0 to 1, and that will be all of my likelihoods. And if I plot the likelihoods, this is what it looks like. And we see, oh yeah, it looks like it's maximized at 0.61. But don't take my word for it. We can ask R to maximize it for us using the optim function optim. Okay, and so this is the likelihood of 61 heads. It's exactly the same. It's a function of p, and it's just exactly what I have here. Because optim always finds the minimum, and I want to maximize it. I want to find the minimum of -1 times the function. So this is the function I'm trying to maximize, okay? And so this is what I want. And when I run the optim function, it says, okay, the value that optimizes or maximizes your likelihood there is 0.61. So that's what we have. Okay, so that's our maximum likelihood estimate. With Bayesian, and the Bayesian method, we still use this likelihood part. Okay, this part is still useful to us. This is still going to be our likelihood function, but we mix in so the likelihood is still that. And this is the likelihood is the probability of x given your value theta, right? So you vary the theta and you ask what's the probability of getting my data x, and in this case we've summarized the x using the value z. So I guess I should just say probability of my data here. And in that case, that's what we have. We also have a prior probability. Okay, the prior probability represents our quote-unquote beliefs, and I hate to use that word, but it's our beliefs about theta. Okay, so it's prior to seeing the data, what do we believe theta is equal to? Okay, so prior to seeing the data, what do we believe about theta? And this sounds a little bit strange, because if I said, okay, I'm going to show you a coin here, and I say, what's the probability that this coin is going to land heads? What would you tell me? You'd tell me it's 0.5. But I have to ask you, well, could it be something other than 0.5? And you might say, no, I believe all coins land heads with probability 0.5, and you can't convince me otherwise. And if that's the case, then the data doesn't matter, even if the coin lands heads 100% of the time. If you're convinced that all coins are fair, you know, this data will not sway your opinion, right? On the other hand, if you're a little bit more quote agnostic about the coin, you might say, well, I'm thinking it should land heads around 0.5, but you know, I'm open to the possibility that it's not going to land heads with probability 0.5, right? And so we can have prior beliefs. Okay. So prior beliefs. So one possibility, okay, is all coins, you know, the coin lands heads with probability equal to 0.5, and nothing can convince me otherwise. All right. And, you know, this is a situation where you have this 0.5 everywhere else from 0 to 1. This person says it's not possible. The coin, okay? And in this case, then there's no sense in presenting any data to this person with these unconvincible prior beliefs, because it will not be swayed, right? The prior probability of being anything other than 0.5 is 0, so it's not possible to be anything else. Okay, so this would be data will not affect the beliefs here. Okay, so if you this is like kind of getting into an argument with someone who is unwilling to change their opinion about something, okay? And if you have somebody who is unwilling to take in, you know, new evidence or whatever, then you know, there's no swaying, right? And this is partially why, you know, online Facebook comment wars are useless. Okay, but you know, we could have. I'm pretty sure, you know, I'm fairly confident the coin lands heads. You know, around 0.5, okay? But it could be different, all right? And so in that case, you might have something that looks like this is supposed to look like this, okay? Between 0 and 1, and we're convinced around 0.5, you know. Or from the beginning, you can have a very skeptical, or you might say like I think coins land heads more often than 0.5. You know, this all comes into the prior beliefs, right? So other priors, you can have something that looks like this between 0 and 1 as far as coins go. You can have this would be a flat prior. This is the quote uninformative prior. Meaning that, you know, any value between 0 and 1 is possible. This is like you've never seen a coin before and you have no idea how a coin works. And so you say, okay, well, it could happen anywhere between 0 and 1, right? And it doesn't even have to be these nice shapes. You know, if you have a very strange experience with coins, you know, sure, you could have this, right? There's no rule against that. It's, you know, this you know, I don't know what life has done to you to make you believe this about coins, but if that's what you believe about coins, then that's fine, okay? But you know, generally the nice for coin flips, you know, a beta distribution is a common choice, okay? And there are actually nice mathematical properties about the beta distribution, and we call this a conjugate prior. Conjugate's it's a I don't know. It's an interesting word, right? Okay. Conjugate prior, meaning it has it meshes well with conjugate prior for the Bernoulli binomial, right? Okay, so let me just kind of plot some of these prior beliefs and how this might look, okay? So if so here's a possible prior for P, okay? And so I can just do, and so these are just all different beta distributions. Okay, so this is one where, and I'll just do all of these. So these are all, maybe I'll do this one in blue. Okay, so these are both ones where you're kind of expecting it to be at 0.5, but this one, the first one in black, indicates that you're pretty confident that it's 0.5, okay, and you will permit between 0.4 and 0.6 a little bit more readily. The blue line represents like 0.5 is your best guess, but you would permit anything really from 0.15 to 0.85 for coin flip, okay? And perhaps, you know, you might be someone else who thinks it's very much has to be 0.5, and in this case, your prior would be very thin at 0.5 there, okay? And I guess I can okay. So it's, you know, this is a very thin thing, but it's also not, so you have a very sharp spike at 0.5, but it's also not 0 everywhere else, okay? So this would take you a lot of convincing to say it's something other than 0.5, okay? But, you know, if you were very uncertain about coins and you had no idea, then you could do just a different prior. Okay, and this would be a flat one. You can also have, I'm running out of colors here, you know, ones that indicate, you know, maybe you think the coin is biased to begin with. Okay, and so over here, you know, you're thinking, okay, it's going to be somewhere over there. Okay, so these could all represent your prior beliefs. What we want to do in Bayesian statistics is we mix what we see in the data with what our prior beliefs were. Okay, and so there's a balance. If your prior beliefs are very strong, it's going to take a lot of data to kind of shift those prior beliefs. If your prior beliefs were not very strong, then whatever data you see will convince you. And so the way we find the mix between the prior and the likelihood, this is what we call our posterior distribution. So the posterior distribution, which is the probability of theta given our data x, this is using Bayes' rule. Is this, okay? It's the likelihood times our prior beliefs divided by the posterior. Now the posterior does not depend on theta, and so this ends up just being a constant, and it's the multiplicative constant so that the numerator integrates to 1. Okay, that's all it is. And so let me just give you a few demonstrations of this. Okay, so I can plot our so this is the likelihood. Whoops. Okay, let me just. All right. So this black line is kind of the likelihood if we flipped the coin 10 times and it landed heads 5 times out of 10. Okay. This is the likelihood if I flip it 100 times and it lands heads 61 times. Okay. And the difference between these likelihoods is that, you know, likelihoods are not probability distributions, because probability distributions have to integrate to 1. Likelihoods do not have to integrate to 1, okay, across all of the parameter values. And so to normalize our likelihood, I would kind of do a little bit of, you know, integration here, and now this kind of works out here. Okay, let me just show you. Where did this go? Okay, so right here, the blue represents our likelihood. The black is our prior beliefs. Okay, so according to our prior beliefs, it should, I'm thinking the coin, perhaps I should plot these in a certain order, but we're saying the coin should land heads with probability 0.5. I look at my likelihood. The likelihood says, according to just the data we've seen, it should land, the coin should flip heads, you know, with probability 0.61. And so the combination of those, my prior beliefs mixed in with the likelihood, gives me my posterior, which is kind of a blending of the two. Right? If my prior was much weaker, okay, so here my prior beliefs are the coin should land heads around 0.5, but I could be easily swayed otherwise. Okay, if this was my prior beliefs, you know, I still have the same likelihood here in blue, and so the posterior is a kind of a blending of my prior beliefs and the likelihood. And because the data weighs a lot more heavily, my posterior beliefs resemble my data likelihood a lot more. Okay, so this is where I had, you know, stronger prior beliefs. This is where I have, this is the likelihood. The likelihood is actually the same in both of these cases. It's just scaled a little bit differently. But we can see how the posterior, you know, here is like halfway between, and over here is a lot closer. Let me try another set here. so here, okay, you can't see this. This is if your prior beliefs, let's say you had weird beliefs about coins and you were like absolutely convinced that coins land heads with probability 0.2, okay, and it's a very strong belief. So there's this sharp point right there, okay, and you take a look at your likelihood, which says, you know what, our likelihood says they land heads around 0.6, okay. If your prior beliefs are very strong, this amount of data probably won't convince you, and so it affects your just a tiny bit, and it shifts it over. And maybe I colored this in wrong. Oh, this was my prior beliefs. I had this. The black is the prior beliefs. I should have. So this is the prior. Okay, this is your prior beliefs. This is your likelihood, and thus your posterior is kind of I don't know if you can see. It just gets shifted over ever so slightly because of the data that you've seen. However, if you have a bunch of data, okay, like if you observe thousands of coins, okay, thousands of coin flips, then that would affect what you're more likely to accept as a convincing argument here. Okay. So this is kind of what we're going for in all of this. So far, we've been looking just at a single univariate case, but if we have multiple variables, it's just the same, okay? And so let me just talk about a multivariate case where we have independent let's say we have two coins that are independent of each other, okay? So we can talk about kind of a multivariate case, all right? And so here we have two independent coins, okay? And so we can have kind of sample one from coin one, and we would say, you know, we have N1 flips, Z1 heads, and our likelihood, and parameter theta 1. Theta 1 is our probability of heads for coin 1. Okay, and so our likelihood would be theta 1 to the Z1, 1 minus theta 1 to the N1 minus Z1. Okay, and then we have sample 2 from coin 2. All right, and so far we've been talking about coins and landing heads, but this could be generalized to any categorical variable and groups of people. So it could be group 1, sample 1 could be, you know, these people got the drug, and sample 2 got the placebo. And we want to know, you know, is there a difference in the probability of, you know, improvement for sample 2 versus the probability of improvement for sample 1? If we've got, you know, and effectively you're just going to say, you know, you can treat these people as if they were the results of coin flips for random cases here, okay? And so if they're independent coins and our samples are independent, the coins are independent and the samples are independent, then the likelihood of kind of the data given theta 1 and theta 2 is going to just be the product of these things. Okay, so we can just say theta 1, z1, 1 minus theta 1, and 1 minus z1 times theta 2 raised to the z2 times 1 minus theta 2 to the n2 minus z2. Okay, because these themselves are, so this is the likelihood, right? And then we have to consider kind of the prior distribution. So the posterior, if we want to know, okay, so this is the likelihood of our data. I'm going to go ahead and copy this onto the next slide. You don't have to copy it again in your notes. But we would have the posterior is going to be the probability of theta 1 and theta 2 given our data, right? And so this is going to be the likelihood, the data, given theta 1 and theta 2 times the prior. And so the prior is just a distribution on theta 1 and theta 2. Now this is a two-dimensional, the prior is a two-dimensional distribution for theta 1 and theta 2. Okay, and then we would divide this by the probability of the data. Okay, the probability of the data, again, this would be complicated. The probability of the, quote, the marginal distribution, which is the probability of the data, is technically, it's complicated, and it's the, the double integral of the data. What is it? It's basically the double integral of the numerator across all possible values of theta 1 and theta 2. Okay. Basically, it's just kind of like, the rule is we need everything to add up to 1, right? And so if you think of the integral as a summation, okay, and you can kind of think of the integral as a summation. It's just, okay, we want to sum across the entire 2D space. And what is that entire space? You get a value there across all possible values of theta 1 and theta 2. And just so that everything adds up, indeed, to 1, you just divide by whatever this thing comes out to be, if that kind of makes sense. So it's just as if you're going to find every single possible value, and you just want that whole thing to add up to 1. So you're just dividing. But again, multiplicative constant, this is what Monte Carlo's methods are all about. We're just trying to avoid having to do this crazy double integral thing, right? Okay, so the prior is going to be a two-dimensional distribution for this. Now, we can take a little bit of a cheat. It's not a cheat. It's just, if we say the coins are independent of each other, then we can just say, well, then the prior is just going to be a product of the two priors themselves. Okay, so if the coins are independent, or if the two groups are independent, then the probability of theta 1 comma theta 2, the joint distribution, which is basically like an and, but it's a probability distribution, is going to be the distribution of the prior distribution on theta 1 multiplied by the prior distribution of theta 2. Okay, so you've got a beta distribution for theta 1 and a beta distribution for theta 2, and now we're working in two-dimensional space here. All right, and now we want to, combine all of this so that our posterior, we can just say our posterior now is going to be proportional of theta 1 comma theta 2, given our data, is proportional to, so we'll say it's proportional to the likelihood, which we have up here. Maybe I'll copy this, okay? proportional to this, I'm going to run out of space, times the prior on theta 1 and the prior on theta 2. Okay, and we can apply, you know, we can say these themselves are beta distributions. Okay, I guess we'll take a further look at this on Monday. Right?
What's the range of